Welcome to solverfy.
All right, we're looking at question 28.34, and we have this semicircular current of wire, and we're looking at point P, and we want to find the magnitude and direction of the magnetic field at point P. So we're going to need to use the Biot-Savart law, which I've written down up here. And the key components that we have, here's the constant out in front. I is the current. DL is going to be the little section of wire, the segment that we're looking at along the length of the wire. And sine of phi, the angle, is going to be the angle between R, which is going to be the vector pointing to the point that we're looking at. So that's going to be R here, and DL. So first, let's think about these straight sections of wire here. We have so this term right over here, where we have I times DL times R times the sine of this angle. This is really a cross product, and the cross product is between DL and R. So we want to look at these two red vectors here. So when we're looking at these straight sections, we're going to have DL is just going to be along just a horizontal line, just like this. So this is going to be our DL, and our R is going to be just pointing directly horizontally out in the other direction. So our DL and an R are going to be parallel, and the cross product between two parallel lines is going to be 0. And the same situation is going to happen over here. The DL and the R for this straight section of wire, they're both parallel, so the cross product is 0. So these straight segments are not going to contribute anything to the magnetic field at point P. So we're just going to totally ignore them. Now this semicircular section here, when we look at DL at any point, it's going to be the tangent to this semicircle. And then R is going to be along the radius of the circle. So DL and R are going to be perpendicular at every point in the semicircle. So sine of theta, or sine of phi here, when we're saying that we're looking at this angle between DL and R, sine of theta is really just going to be 1, because sine of 90 degrees is 1. So we can actually just get rid of this angle term here and not worry about it, because it's just going to be equal to 1 for the entire integral that we have to do here. So let's just plug these in terms of the things, the terms that we know. So we know that R, our little r here, is going to be equal to the radius of the semicircle, which is just capital R. And we have the current. I guess the current is just listed as I. So let's just rewrite this just using our capital R, just to be totally explicit. So we can plug everything in to what we have. Now notice that all of these terms except for DL here we know and are going to be easy to calculate. We're just going to have to plug in. But now what we have, we're going to need to integrate this expression, and the only thing that we're integrating over is DL, since everything else is a constant. So let's just simplify this a tiny bit. We have R divided by R cubed, which is going to end up with just a factor of R squared on the bottom here. And again, since all of these are constants, I'm just going to pull this DL term all the way out to just make this really explicit that we have all of these are just constants, and we have this DL. So when we integrate this, what we're going to want to do is integrate dB to get regular B, and we're going to need to integrate DL. Now, when we integrate along DL, DL is just this semicircle. So all we need to do is calculate the length of this segment. Remember, this is just half of a circle with radius r. So the circumference of this entire circle would be 2 pi r. But since we're just looking at this semicircle, this DL is just going to be equal to is going to be equal to just pi times capital R. So if we, once we integrate this here, on the left, integrating dv is just going to give us b, which is exactly what we want. We have all these constants here, just as before. And then remember, integral of dl is going to be pi times our capital R. Now this is written a little bit messy, so let's just simplify this. I'm sorry, this is capital R. So when we look at all this, we have a factor of 4 pi down here and a factor of pi up here. So we're going to cancel these out like this. And we have r squared times r, or a denominator is r squared down here and a factor of r up in the numerator. So we'll cancel that out. That's going to leave us with 1 factor of r on the bottom. And then rewriting this all into one fraction, we'll have mu naught times I on top, and then 4 times r on the bottom. So this is going to be our final expression that we are going to want to, that will give us the current of the magnitude of the magnetic field at this point P from this current. Now let's think about the direction. Again, these little, the straight pieces on either end aren't going to contribute any magnetic field, so we can ignore them. And again, thinking about the direction of the magnetic field, we want to take the cross product of dl and r. So if we point our thumb in the direction of the current here, so along the outer edge of the circle, notice that no matter where on the circle we are, our thumb is going to be pointing to the right like this up here. Our fingers are going to curl into the page at point P. So regardless of where on the circle, this is all contributing magnetic field pointing into the page, and this is going to be the magnitude.